Today we are going to learn how to find out eigenvectors for a given matrix. We need to solve the determinant of A minus lambda I equal to 0 to get the eigenvalues. We know that I is an identity matrix and lambda is a scalar. So this determinant A minus lambda I changes A by adding along the diagonal elements the lambda terms. So it becomes now determinant of 1 minus lambda and then minus 1 minus lambda and again minus 1 minus lambda along the diagonals, and rest of the elements have no changes over here. So now this determinant should become equal to 0. So on expanding, we expand along row 1, we know that the signs for those are positive, negative and positive. So 1 minus lambda multiplied with the determinant of the second and the third column. So we have the determinant of minus 1 minus lambda, 0, minus 2, minus 1 minus lambda. And this is also called the cofactor of this first element. Right? Then, now, the next element is minus 2. So minus 2 multiplied with the determinant of first column and the last column, which is 6, 0, minus 1, minus 1, minus lambda. Then plus 1 times 6 minus 1 minus lambda minus 1 minus 2. And we have written this here equal to 0. So let us expand this one. So on expansion, we have 1 minus lambda. And here we can notice that both of these diagonal elements are same. And we have minus as a common term. On multiplying it becomes plus. And simply we have 1 plus lambda whole square. And we should have a minus here. And then when multiplying these two, it becomes 0. So I am omitting that step. The next step is minus 2 times. So it is minus 2 times. We multiply this 2. It becomes minus 6 and minus 6 lambda. So it is minus 6 lambda minus 0. So minus 0. Right? Then plus 1 times. If you multiply this, it becomes minus 12 times minus. We should notice here we are putting this minus in between as we do in all these steps. Whereas when we here multiply these two, we can notice that both the terms are having minus signs. So on multiplication, it becomes plus. So, but we should be very careful when writing that one. So it is 1 plus lambda within the parenthesis. So notice that this minus is common for both. So if we do carefully, we will not have a mistake. Okay, so this is 0. Now 1 minus lambda multiplied with 1 plus lambda square. If we expand that, I have 1 plus 2 lambda plus lambda square. Now if I multiply this, it becomes plus 12 and then plus 12 lambda. And then this is 1 times these values. It is going to be same. So it is minus 12 minus 1 minus lambda equal to 0. Right? So right now I can strike plus 12 and minus 12. This minus 1 will be there. We'll look at it later. Now if you multiply this with all these three terms, we have 1 plus 2 lambda plus lambda square. And then multiplying with minus lambda with these three terms, we have minus lambda minus 2 lambda square then minus lambda cube. Then we have plus 12 lambda, plus 12 lambda, then minus 1, then minus lambda equal to 0. Let us continue expanding further. Okay, so I just moved a little lot. Okay, now we have the highest power being minus lambda cube. So minus lambda cube, we are writing it as a first term. And we can notice that there are two lambda squares. One is 1 lambda square and minus 2 lambda square. So it sums up to be minus lambda square. Then we have lambda terms. So we can find here 2 lambda, and then here I suppose I haven't written this 12 lambda here. Did I write minus 12? So I suppose I have forgotten to write this 12 lambda. So this should be 12 lambda, right? Okay. So minus lambda. So now it becomes 12 lambda minus lambda, and then here 1 lambda is there. So 14, and then here 1 minus lambda. So let me clear it once again. Here there is 2 lambda, there is 1 lambda in negative and 1 lambda in negative. They all cancel, and we are only left with plus 12 lambda. So plus 12 lambda equal to 0. And we don't have any constant because this 1 and here this minus 1, they cancel. Now if I multiply by minus, so I have a cubic equation, lambda cube plus lambda square minus 12 lambda equal to 0. Now I can take this lambda as a common term. Now we'll have lambda square plus lambda minus 12 equal to 0. Right? So naturally, one of its root is going to be lambda equal to 0, and we will call this as first eigenvalue, otherwise lambda 1 equal to 0. The first term. There is no point there to say this is first. Any number can be taken as a first, second or third. So let us have this as lambda 1. Now on solving this quadratic equation, we have the last element as minus 12. If I split minus 12 as 4 into minus 3, on multiplying I will get minus 12 back, and on adding I'll get the middle number plus 1. So I can rewrite this as lambda plus 4 times lambda minus 3 equal to 0. Therefore, I have the second lambda value, eigenvalue, as lambda 2 equal to minus 4, and the third lambda value as lambda 3 being 3. So now we have got 3 lambda values, lambda equal to 0, and then lambda 2 equal to minus 4, and lambda 3 equal to 3. So the eigenvalues are 0, minus 4 and 3. Now we need to find out the eigenvectors corresponding to the eigenvalues, lambdas taking the value 0, minus 4 and 3. For which, let us go back to our matrix A minus lambda I determinant. So in this determinant, if I am substituting lambda to be equal to 0, then these lambdas will be 0. Then I will be just having the same matrix here. So the determinant of A minus lambda I is just nothing but the determinant of A. So let me write here the eigenvector corresponding to lambda equal to 0. So the eigenvector for lambda equal to 0 is determinant of A minus lambda I, so which is nothing but the determinant of A, which is 1, 2, 1, and then 6, minus 1, 0, and then minus 1, minus 2, and minus 1, whose determinant, okay, is a 0. Whereas we need to solve this equation, that is A minus lambda I times x equal to 0. So which means this is a systematic equation where you have this in the matrix form, and the x is x1, x2, x3, which is equal to 0, 0, 0. Let me write simply as 0, single 0, right? So now further continuing, so we can reduce this matrix along the rows. So it is called row reduction. So what we are going to do is row reduction. So when you reduce along the row operations, so row reduction is done through row operations, right? So row operations are just multiplying one row with a scalar and adding with one row with another scalar. Say, for example, I have a scalar A and B, and I have two rows R1 and R2. Then what I can do is I can replace any of these one row by A times R1 plus B times R2. So this is a new row which will be replaced by either row 1 or row 2, depending upon the situation. So when we are doing this row reduced matrix, okay, what we need to do, we should keep in mind that we are going diagonally. So how to go diagonally is, first we should have this element to be 1, or it need not be 1 also. If it is 1, naturally we can have 1 here. Otherwise, we can divide by any number and convert it to 1. But I generally don't do that one. All I do is, I take the first element, make these two elements down this first column as zeros. Then we'll go diagonally. The second element is minus 1. Make the upper and lower values as zeros. And then go along the diagonal and keep this value as a reference value and make these two elements as zeros. Let us do that one. Now let us continue the row reduced operation. So what I am doing is, I am going to convert zeros. So if I take R2 down 1, we have 6 here. So if I multiply the first row with minus 6 and add, it becomes a 0. So what I am going to do is, let us not multiply by minus 6, let us multiply by 6. So 6 times R1, what happens? it is 6 1 is 6, 6 2s are 12 and 6. Then R2 I am going to write same, which is 6 minus 1 and 0. So down, if I subtract 6R1 minus R2, what happens? 6 minus 6, it is 0. 12 minus of minus, so it is becoming plus, so it is 13. And 6 minus 0 is 6. So now I can replace that in row 2. So replace this one along row 2. Right? Once again, let us do the same row operation for row 3. For row 3 it is very simple because here we are having minus 1 and we are having R1. So if we add R1 with R3 it becomes 0. So let me add R1 with R3. So what we have is 1 minus 1, it is 0. 2 minus 2, it is once again 0. We are lucky that we are getting all the 3 values to be 0. And let us replace this with R3. Now R2 and R3 are replaced with new values. So R1 there is no change, 1, 2, 1. R2 I have 0, 13 and 6. And R3 is 0, 0, 0. Then multiplied with the column matrix x1, x2, x3 equal to 0. Now it becomes really simple to solve the simultaneous equation at this stage. We can further reduce by converting this element as 0, but let us not do that one. So if I back solve it from the last, I will be easily getting the solution. But before that, let us write the multiplication of these two. 1, 2, 1 multiplied with x1, x2, x3. I have x1 plus 2x2 plus x3 equal to 0. And then 13 times x2 plus 6x3 equal to 0. Now I can write 13x2 is equal to minus 6x3. So I am writing 13x2 equal to minus 6x3. Otherwise I can write x2 to be equal to minus 6 by 13 x3. So if I am going to put minus 13, I can cancel this. So I am going to put x3 equal to minus 13. Usually people put 1 here and put it x2 value in the fraction, which is also permitted. But let me put x3 equal to minus 13 so that x2 becomes plus 6. Plus 6. Now, if I substitute these values in the first equation, I will have x1 plus 2 times x2, which is 6, plus x3, which is minus 13, equal to 0. So this is x1 plus 12 minus 13 equal to 0. Otherwise, x1 minus 1 equal to 0 or x1 equal to 1. Therefore, the eigenvector corresponding to lambda for eigenvalue lambda equal to 0 is 1, 6 and minus 13. Okay. Some textbook they write it in a reduced form by using x3 as 1, so that x2 will become minus 6 by 13 and this will become 1 by 13, right? So that is also allowed. We can write in any form because we have infinite number of eigenvectors, okay, and all such vectors are spanned by the vector we choose. So spanning of vectors are nothing but if you multiply this by 2, we'll have 2, 12 and minus 26. So that will be one another eigenvector. If I multiply by 3, we'll have 3, 18 and minus 39 to be another vector. Like that we can have infinite number of vectors and we call this as a spanning vector, right? So let us find out the eigenvector for the remaining values. Now let us find the eigenvector corresponding to the eigenvalue lambda equal to minus 4. So all we need to do is to put minus 4 in this matrix. So if I put minus 4, I have 1 minus times minus 4, it is 1 plus 4. So I have 5 and then 2, 1 and 6 here. Minus 1 minus 4 times minus, which is plus 4. 4 minus 1 is 3. So I have 3 here and then 0. Then minus 1 minus 2 and once again 3 here. Now this is multiplied with x1, x2, x3, x3 and then the right hand side is 0. Okay, so now let us continue. So by row reduction. So what is a row reduction I'm going to do is I'm not going to change this 5 as 1. So if I divide the first row by 5, it will become 1. Many textbooks follow that idea. So I never do that one because I like to avoid fractions. So what I do is I multiply. All we need to do is to make this value down 5 as a 0. So we should make 6 to be 0 and minus 1 to be 0. So first we will concentrate on the second row. So what I can do is I can multiply the first row with the 6, it becomes 30, and second row with 5, again it will become 30. So row 1, if I multiply with 6, I will have 6 5s are 30 and 6 2s are 12 and 6 1 is 6. Then if I multiply R2 with 5, then I have 5 R2 to be equal to 6 5s are 30, 5 3s are 15 and 5 times 0 is 0. So if I subtract, I get 30 minus 30 0, 12 minus 15 as minus 3 and 6 minus 0 is 6. And this is the new one which we can replace it with the second row. So this operation is replaced with the second row. Now let us do this first and then later we can continue for the third one. So if I replace the second row, I get 5, 2, 1 and I have 0, minus 3, 6. And then the last row is minus 1, minus 2, 3 multiplied with x1, x2, x3 equal to 0. Now our next target is to make this element minus 1 as 0, which is very simple, like keeping the row 1 as it is. Row 1 is 5, 2, 1, and row 3 can be multiplied with 5. So we'll get 5 times row 3, which is minus 5, minus 10, and 15. So we know that we can get a 0 by adding. So R1 plus 5 times R3 will have 0, minus 8, and 16. So let us replace this with the third row to get the new matrix. So the new matrix is 5, 2, 1, 0, minus 3, 6, and we have a 0, minus 8, and 16 multiplied with the column matrix x. Let me write x here for simplification, right? Now you can notice that here, the next step is to make zeros above minus 3. That is, we have to make this term as a 0 and down this term as a 0. So that I can do it by multiplying the first row with 3 and the second row with 2. So what I'm going to do is, I have stuck up with the pen, just a minute. Yes. So now let us replace the first row once again. So row 1 we are multiplying with 3, so that I will have 6 here. So I need to make this term as 0. So we made zeros down the first element. Now the second diagonal element is the minus 3. So we have to make zeros on the upper and lower values. Therefore I am multiplying by 3. So 3 times R1 becomes 15. 3 2s are 6 and 3 1 is 3. Now R2 I am multiplying by 2. So 2 times R2 I will have 0, minus 6 and 12. And when we add these, I have 15, 0, and once again 15. And let us replace this with R1. So the new value of the R1 will become 15, 0, and 15. Then what next we can do is, we can make this fellow as a 0. Okay. However, I suppose I don't want to do that one, because we can simply get 8x3 equal to 16. No. Let us make it as 0. Okay. So what we can do is, we can multiply the second row with R2 is multiplied with 8. So 8 times R2 get 0, minus 24, and 48. 0, minus 24, and 48. And R3 is multiplied with 3. So that I have 0, once again minus 24, and minus 48. Plus 48. So when I subtract, all these terms are becoming 0, and we are replacing the third row with these elements. So now we will have the new matrix to be 5 2 1. So 5 2 1. I suppose it is not 5 2 1, it is 15 0 and 15. Of course, we can write it as 1 0 1. We'll later rewrite. Then second row is the same, 0 minus 3 and 6. And third row is simply 0 0 0. And if I replace this into 1 0 1 and 0, and if I divide by 3 or minus 3, I will get 1 and minus 2, and this is 0 . So I have, just a minute, I stuck up with the writing pen. So you have 0 0 and 0. This multiplied with x1, x2, x3 equal to 0. Now if I multiply, I have x1 plus x3 being 0, and then the second one, it is x2 minus 2x3 is 0. So x2 minus 2x3 equal to 0. So from the last one, I have x2 being equal to 2 times x3. So if I put x3 to be 1, naturally I will get x2 equal to 2. Now if I am substituting x2 equal to 2 here, I should get x3's value as, I suppose there is some mistake over here. So from this equation we identified that x3 equal to 1. So if I put x3 equal to 1, then I am naturally going to get x2 equal to 2. Now going to this equation, so we'll have x1 equal to, so this is not minus actually, so when I was marking it became minus. Okay, right. So x1 equal to minus x3, and we know x3 we have taken to be 1, so x1 is equal to minus 1. So our eigenvector, what is the eigenvector here? Vector is x1 value is minus 1, x2 is 2, and x3 we have taken 1. So this is the eigenvector that corresponds for the eigenvalue lambda equal to minus 4. Now finally let us continue our discussion to find out the eigenvector for lambda equal to 3. I suppose the third value is lambda equal to 3. So if I substitute lambda equal to 3, I will get minus 2, and then 2, 1, then 6, minus 1 and minus 3 becomes minus 4, and then 0. Let me take some space. Okay. We have to go to the next page anyhow, let it be. So here this is minus 1, then minus 2, and this is once again minus 4, multiplied with x1, x2, x3, and the right hand side is 0. I suppose by this point onwards you can very easily continue. So let me continue and explain. But still, what I would expect from you is you can pause the video and do it for yourself from this point, and then check whether the steps which I am doing is matching with your answer. So that will be a learning point. But still, I am going to continue to solve the complete problem. Right? So here I have replaced the previous page. So let me change the page width. Yes, right. So now what we can do, the same rule where I'm going to apply. I'm going to make this 6 as a 0 and this minus 1 as a 0. So this is row 1, row 2, row 3. So I never go for making this as 1 because we will be having difficulty with fractions. So right. So let me multiply R1, complete R1 by 3 so that it becomes 6. So 3 times R1 is minus 6. 3 2s are 6 and 3 1 is 3. R2 we are going to keep the same. So this is 6 minus 4 and 0. So when this is added, it becomes 0. So when we add, we are getting this one, and this new value we are going to replace it along row 2. Now for the third row, it is enough if we multiply the third row with 2 and then subtract. So R1 here going to be same, R1 is going to be same, that is minus 2, 2, 1, and R3 we are going to multiply with 2 so that it becomes minus 2, minus 4 and minus 8. So on subtraction it becomes, we are subtracting here, okay. So R1 minus 2 R3. Here I forgot to mention what we are doing here. Here we are adding. So 3R1 plus R2 here. Right? So this is R1 minus 2 R3. So if I subtract, this becomes 0. This becomes, on subtraction, this becomes plus 6. And this becomes plus 9. Okay. Right. So now still what we can do is we can reduce this further by dividing by 3. Okay, so this is not necessary, but it's still, if you want, you can do that one. So if I divide by 3, it is 0, 3 2s are 6 and 3 3s are 9. So this is the new value of the third row. Right? So let us continue and replace the row values. So the first row is minus 2, 2 and 1. And the second row is 0, 2 and 3. And the third row is 0, 2 and 3. And we can very well see that the third row on the next operation can be, third row is the same as second row. So we can very easily change it to this form, which is 0, 2, 3 and 0, 0, 0. So here remember that there is one x here and the right hand side is 0. Okay, so that is always there. So sometimes I forget to write. So this x equal to 0. Now what is the reduced form of the equation? It is simply minus 2x1 plus 2x2 plus x3 equal to 0. We can still reduce. I can make this one as 0 and then proceed, so that it will be simplified. Okay, so that is what I was doing in the earlier case also. Okay, so because this looks something simpler, let me continue with this and then substitute, because the moment I get the x2 value, I can substitute x2 value in both and then get it easily. So without making 0 also we can proceed. So here 2x2 plus 3x3 equal to 0, that which means 2x2 is equal to minus 3x3, and so x2's value is equal to minus 3 by 2 times x3. Let us substitute x3's value to be 2. So if I substitute x3 to be 2, this 2 will cancel, so that I can get a integer value for x2. So I am going to put x3 to be 2, so that x2's value is minus 3. Okay, and now you put x2 and x3's value in the first equation, so that we'll have minus 2x1 plus 2 times minus 3 plus 2 is equal to 0. That implies minus 2x1 is minus 6 plus 4, minus 6 plus 2, which is minus 4, which is equal to plus 4. This says that x1 is taking the value minus 2. Therefore, the eigenvalue corresponding to lambda equal to 3. So the eigenvector vector for eigenvalue lambda equal to 3 is this, which is minus 2 minus 2 minus 3 and 2. We can now write all the eigenvectors. So we had the eigenvalues lambda equal to 0, and then we had lambda equal to minus 4, and then we had lambda equal to 3, and then their corresponding vectors, eigenvectors, are 1, 6 and 13. I suppose it was minus 13 if I'm remembering right. So 1, 6 and minus 13. Then for lambda equal to minus 4, I have to go and check. So kindly check that one. So minus 1, 2 and 1. I suppose my memory is right. That was the answer we got. And for lambda equal to 3, minus 2, minus 3 and 2. Right, so this is the end of the session. I hope I have not missed any step. So this is actually row reduced form. Without row reduction also, what we can do is you can use Texas calculator, or even you can use some kind of 991 MS calculator that we use in India. All these calculators, they are very good in solving simultaneous equations. Okay, the only point where we have is when the solutions are not unique solutions. So here we are having infinite solutions, no? So when there are infinite solutions, Indian calculators they don't give proper solutions. They will show you errors. But Texas calculators, they give you eigenvectors and eigenvalues given very easily. Thank you. I believe that my video is very lengthier. but no other go. My voice is not that good, and I am not able to speak in a quicker manner. And thank you. If you have further doubts or if you need any other new concept to be described, kindly let me know. Bye for now.